and its power generation in pilot scale dual chamber PFC. So what is PFC? PFC is the integration between two emerging technologies, which is the photocatalysis and also the fuel cell technologies. It is being used to degrade wastewater, especially organic pollutants such as formalin and also synthetic dry wastewater. Simultaneously, it will generate electricity by recovering the chemical energy from the wastewater. The key components in the PFC system include the photoanode, the cathode, and also aqueous medium and the light source. Although the PFC has been proven to be able to degrade the wastewater, simultaneously generate electricity, but the research on the pilot scale dual chamber PFC has not been done, as the scale-up process, the degradation of the organic wastewater and its power generation has yet to be discovered as well. So, for my objectives of this project is to test the pilot scale of the dual chamber PFC at 1 liter, 2 liters, and 4 liters by using the zinc oxide/zinc photoanode to evaluate and measure the degradation efficiency and its power output. Let us understand how the PFC works. It works by the photoexcitation process, whereby it occurs during the irradiation of the light onto the surface of the photoanode, thus producing the photogenerated electrons from the valence band to the conduction bands, and then the photogenerated electrons from the conduction bands will travel through the external circuit to generate electricity by reaching to the cathode side. Then, for the radicals production, the photogenerated electrons that has reached to the cathode chamber will react with the oxygen molecule to produce the superoxide radicals, while the photogenerated holes at the valence band will react with the water to produce hydroxy radicals to degrade the wastewater. In order for us to understand how the volume of PFC affect the PFC performances, several factors have been set to be constant, which includes the light intensity to be at its optimal condition at 1000 to 1300 lumen, the initial concentration of wastewater to be at 10 ppm, and the initial pH to be at acidic condition, specifically pH 4. Then the concentration of the sodium hypochlorite to be at 250 ml per liter, and the cathode chamber should be aerated with oxygen. Generally, the contact hour of the PFC system should be around 4 to 8 hours. For the methodology part, the zinc oxide/zinc photoanode was being prepared by using the electrochemical deposition method, whereby the zinc foil will be cut into desired dimension, and then it will be connected to the cathode side of the direct current, and having a graphite plate at the anode side, and both will be submerged into a solution of 0.05 moles zinc acetate and 10% potassium chloride. After constant stirring for 5 minutes at 5 volts, the photoanode will be taken out and rinsed with still water, and then put into the oven to dry it at 120 degrees Celsius for 24 hours. As for the conditions of the pilot scale dual chamber PFC, it is following exactly like the literature review part. This is how my dual chamber PFC setup looks like. For every 1 hour, the sample of the wastewater will be taken, and then the voltage will be recorded by looking at the voltmeter through changing the various resistance value until complete degradation has been achieved. For the evaluation part, the SAM analysis of the photoanode was done to see the before and after changes, and then the power density gas current density graph was plotted to see the power output of the PFC system, while the uv-vis spectrophotometer is to be done to determine the degradation efficiency. So for the result part, before the immobilizations, you can see that there are a circle structure in figure A, while there are stacking of zinc oxide shows in figure B. As for those two is in lower magnification. However, in C and D, we can see that in higher magnification that the zinc oxide particles are in flower form as stated in the literature review. So after the immobilizations, we can see that the zinc oxide has shown some dissociation, although the zinc oxide is still intact onto the surface of the photoanode in flat-like structures. For the color removal efficiencies, we can see that the 1 liter PFC having the highest color removal efficiency, followed by 2 liters and 4 liters. This is because the amount of light reaching to the photoanode surface has been decreased. This is because the distance between the light source and also the photoanode was not fixed in this project. So we know that the light from air density reaching to the water density, it will be scattered around. So if the PFC volume increases, meaning that the distance needed to be traveled by the light to reach the photoanode surface is it will cause the light to become more scattered. And then not only that, but the material structure in the wastewater is able to absorb the light. So if distance has been increases, then the material is able to absorb more light onto the limit it from reaching to the surface of the photoanode surface, and then cause less photo excitation to occur. After that is the material used as the chamber is not the same as well. Because the 1 liter PFC and also 2 liter PFC, I'm using the polyethylene terephthalate, which is more transparent and optical clarity, while the 4 liters I'm using polypropylene properties, which allow less light to pass through. And then the distance between the photoanode and the untreated wastewater has also been increased because the size of the PFC chamber has been increased. So the furthest distance between the untreated wastewater to the photoanode surface, which is whereby the formation of hydroxy radical will occur, has been increased. And then the PFC system is in stationary conditions, which means that it solely depends on the diffusion of water to move the hydroxy radical to reach to the untreated wastewater. Lastly is the concentration of the oxygen is different. Although the flow rate of the air pump has been said to be the same for all 3 chambers, but the larger volume of PFC means that the same amount of oxygen are needed to be distributed over a larger area, which leads to a dilution effect. Okay, so we can see that the 1 liter PFC requires 6 hours to completely degrade, and 2 liters require 7, and 4 liters require 8 hours. As for the kinetic photocatalytic degradation, it also shows that the 1 liter PFC has the highest photo degradation efficiency at 0.4366. For the power generation, we can see again the same trend, whereby the 1 liter PFC will have a higher power density, followed by 2 liters and also 4 liters, which is because the higher volume of PFC will have higher possibility for current leakage to occur. This is because the photogenerated electrons being produced will require to travel through a much longer distance to reach to the cathode chamber. And then which means that the photogenerated electrons is more susceptible to the unintended reactions. For example, the photogenerated electrons will react immediately with the oxygen molecule in the anode chamber instead of travel through the external circuit to the cathode chamber. So when this occurs, meaning that less electricity will be produced because it doesn't travel through the external circuit. And then the electron-hole pair recombination, also another factor, whereby we already talked about before that the concentration of the oxygen is not the same for all 3 chambers, and then in higher volume of PFC, it has a lower amount of oxygen. So when this occurs, that the photogenerated electrons reach the cathode side, we have less oxygen to react with to form superoxide radicals. As we know that the formation of superoxide radicals is very important for us to prevent the recombination of electron-hole pair that can reduce the power output. After that is the photoexcitation process. There we already talked about the same thing, which is the distance between the photoanode and also the light source, which causes less photogenerated electron to produce and travel through the external circuit to produce electricity. Lastly is the limited mass transfer. We know that the formation of hydroxy radicals is nearby the surface of the photoanode. So when this occurs, the formation of concentration gradient also will be around there, and then will lead to diffusion resistance. And this diffusion resistance will lead to higher internal resistance, thus lead to voltage losses and reduce the power output. So in conclusion, it is to be concluded that the higher the volume of PFC, the lower is the degradation efficiency and its power output. As increased volume of PFC will lead to decreased performance of PFC. That's all from me. Thank you.
We should take a breath. Yiizamy, I appreciate your understanding on the project, but I also see that there are many rooms for improvement, especially in your experimental design. Right? When you talk about the degradation efficiency, the color removal, you spend a lot of time in explaining the problems with the design. So you realize that. Why are you not correcting the variations so that the experiment can be represented?
Okay, so actually, because my title is being changed during March, end of the March or early of the March, so I'm trying to rush the project to finish it. And then at the same time, although there is not an excuse for me, But for especially for the material that PET and saw the PP one, I'm using PET for both two of these because the dual chamber PFC setup compared to the setup. And that one. So because if I have a higher volume of PFC in terms of like I want to have like this linear like this configuration is going to be a little bit hard because mostly it is in lower, and then meaning that the height is not available for me to do the put the photoanode. So I have to choose a suitable wall of the chamber to become the PFC chamber lah. And then I try to find, and then I can only find one, which is the rubbish bin. So I just use
Yiizamy, I understand. I'm just curious, when you design this experiment, that should already be in your consideration. What needs to be consistent? Am I right? I mean, this is some good work. You are superintendent. You have a good understanding of the project. It's just that the results, the CTs, it seems very fragile, very fragile because there is an experimental design issue. Okay? So it's just like when you have a house, the house looks good when there is a design issue. It doesn't work, it doesn't stand. But overall, it is good. And the conclusion you draw, I don't know. I need to read your thesis to make a recommendation to you as to how best you should present your thesis so that your thesis can be referenced. Because it's important your work needs to be referenced. So at this stage, it is not strong. The work is not strong for people to reference. So you are looking at pilot scale of 1 liter, 2 liter, and 4 liters. Why are you looking at 1 liter, 2 liter, and 4 liters? In terms of the volumes, is there no other better parameters to represent the upscale?
It's actually because the dual chamber PFC has already been done in previous research. So my research is more to like, I just modify it to become more larger.
Yeah, larger, but then, well, anything when you scale up, it means you become larger. But I'm just considering is volume the right variables you consider in your upscaling. You see, when I want to produce some products, maybe I started with 1 gram in lab. Okay, I will 1 gram. I extract something. I get 0.5 grams. My efficiency is 50%. Okay, so when I scale up, okay, logically, I will get 50% as well. You see, I may not at all because as I scale up, I may have more losses. Okay, so as you scale up, what you have experimented in the lab should also be carried across a larger scale, but it may be compromised. It may be compromised. The system may need to be adapted. But as I see is, you are looking at 1 liter, 2 liter, 4 liter. You are looking at, can you maintain your efficiency? Given that your scale at 1 liter, when you scale up at 2 liter, the design has to be comparable. But as of now, your 1 liter and 2 liter and 4 liter, the designs across are not comparable. So you cannot actually even make a conclusion whether you can maintain the efficiency. You get what I'm trying to say?